Where we left on the last video was the Ptolemaic geocentric model, this picture that could explain how everything moved in the sky from the perspective that the Earth was at the center. Now we know that that's not the truth. In truth, our solar system is centered at the sun and everything revolves around the sun. And so in this next video, what we're going to talk about is how that model got developed. Now, when it got developed was following the Renaissance period during the scientific revolution. And we're going to talk about two primary figures here that contributed to this idea. But I wanted to take a second to mention that early astronomers did actually consider that the sun could be at the center. That wasn't just overlooked. The issue was they didn't have observational data precise enough to show that the Earth was actually moving in space. So because they couldn't tell that through their observations, that theory, that hypothesis, could never be shown true. And so they went with what was for them the more simple explanation, that the Earth is at the center and things are going around it. This picture here, before I move slides, this picture was from Copernicus, who we're going to get to in a couple slides. Sol is the word for the sun, and so this is the sun at the center, and so this is the first picture of the heliocentric model. Now, the advantage of the heliocentric model is that it actually is simpler than the geocentric model when you get into the details of how things are moving. Now, from one viewpoint, the Earth-centered view is simpler because it doesn't feel like we're moving and it seems like everything is going around us. But then when you try to fit that model to what's actually happening with the planets, and the sun and the moon included, it has to be pretty complex, and that's where Ptolemy's model came in. Ptolemy's geometric model with the epicycles and the offsets. So to explain everything in the geocentric model gets pretty complicated. It's simpler when you just put the sun at the center. So consider retrograde motion, which we talked about in the last video. That's where the planets are temporarily moving backward in space. Well, that can happen naturally in the heliocentric model when the Earth passes between the sun and that planet. So this path here is Earth's orbit, this is a different planet's orbit, and here's the sun at the center. Now, at point A, if you're on the Earth looking at this planet, you would project it here. And then at B, you'd project it here. But then at C, you'd project it here. So it would have moved backwards. So it's moving from A to B to C, and then going forward to D and then to E. So it makes this sort of loop in the sky. That's what we refer to as retrograde motion. The explanation for it in the heliocentric model is just simple. The Earth is passing underneath that planet. You don't need epicycles. You don't need any offsets that you would in the geocentric model to explain it. So when I say that the heliocentric model is actually simpler, this is what I mean. The first to reintroduce this was Nicholas Copernicus, and it was in 1543. He had access to good planetary data, and he realized that the heliocentric model fit better and was a simpler explanation. But he couldn't prove anything. He still couldn't prove that the Earth was moving. So rather than publish his work as a work of science, he published it as a work of fiction. And this accomplished a couple of things, but the most important of which was that he didn't get excommunicated or killed or imprisoned for life for his blasphemy, because this was against the church's teachings. The church had adopted the Ptolemaic geocentric model. And because he couldn't prove that the heliocentric model was correct, he could just show that it was something that worked and it was simpler, he didn't really have a way to push forward with his ideas. So to sort of save himself, he just published it as a work of fiction. But I think for many scientists of the time, they knew that these ideas were real. It wasn't just fiction. And Galilei was one of those scientists. And he had a tool that would help him actually prove that Copernicus was on the right track. And that tool was the telescope. Galileo didn't invent the telescope, but he was the first one that we know of to use it for astronomy. And his observations caused him to doubt the orthodox teachings of the church and actually give some credence to what Copernicus had said. And the telescope gave him real evidence. Remember our discussion of the process of science. You need to test ideas with evidence. Well, Copernicus had the evidence of how the planets were moving and how his model fit. But the evidence that you'd really need is something a little bit stronger than that to uproot the teachings of more than 1,000 years of history. So here's what the Galileo's first telescope would have looked like, and so let's take a look at what his observations really were. There's 4 that I want us to think about. Jupiter has its own moons. Venus goes through phases, just like our moon does. Saturn has ears, which we know now are the rings. The sun has dark spots that move around its surface. Now, each of these 4 observations is contrary to what the geocentric model would have said for each of these objects. And that's because the geocentric model is built on the idea of circles, that the circle is this perfect shape. The planets move in circles, and so Ptolemy had offset those circles and created epicycles, but they're still circles. Those circles are all in orbit around the Earth, and all of the celestial bodies are moving in this perfect sort of harmony. These 4 observations are contrary to that. If Jupiter has its own moons, they are orbiting Jupiter. That means not everything is orbiting the Earth. If Venus goes through phases, like the moon, why would that be? What's causing the phases? We could explain the phases of the moon because the moon is orbiting around Earth, but the phases of Venus you were not able to explain in the same way. And in fact, they really only make sense when you start thinking that, oh, well, Venus is going around the sun, and so our perspective on it is changing as Venus goes around the sun. The ears of Saturn. So Saturn was not a perfectly circular shape, and so not all of these planets have perfectly circular shapes. And the sun has dark spots. You could think of them as blemishes. It was not a solid one color. And these dark spots we now call sunspots. We'll talk more about what they are later on. But all of these observations told him that the perfection and the harmony was not true, right? There's other details going on. And if the other things can orbit around other things, then maybe the Earth can orbit around the sun. Maybe all of these things can orbit around the sun. And in fact, that model would explain why Venus goes through phases. Now, things like Saturn has ears and the sun has dark spots, those aren't really explained by the heliocentric model, but they are evidence against the perfection of the geocentric model. And so they lead people to consider new ideas for how the universe is arranged and how they come to be, how they form. All right. So now we've seen the geocentric perspective, which is useful to us. We can think of things from the geocentric perspective because we're seeing things from the geocentric perspective. But in reality, we need to keep in mind that really the Earth is moving around the sun. And so if we get to something that doesn't make sense from the geocentric perspective, hopefully it makes sense from the heliocentric one, from the fact that the Earth is moving around the sun. And you'll want to have a pretty good understanding of the fact that the Earth is in orbit around the sun, that the moon is in orbit around the Earth, that the Earth's axis is tilted, and that it's spinning on its axis. Now, there's a lot to keep in mind, but those things are what determine that we have days, how long those days are, that we have seasons, how long those seasons are. So they're intimately integral with our understanding, our fundamental understanding of time and how time proceeds. All right, so what we'll look into next in next week's lecture is more about those orbits and a little bit more into the science of understanding how it evolved from Copernicus and Galileo to explaining the motions of objects in the sky. And we'll get into orbits and the theory of gravity.